Hey guys, I have tried this I don't know how many times and it keeps deleting. So you're getting the selfie version of chemistry that should have been last Thursday. We've been talking about matter. Matter is anything that takes up space, okay? And it has mass, right? We talked about how even air has mass. Gases have mass. Masks are on my mind apparently, and I'm wearing one on my head. All right, if you have any questions about all that, go back and check it out, okay? Now, one of the things I was just reading about was significant figures. If you guys have any questions with that, ask me. You kind of have to forget everything you know about math in significant figures, okay? It just helps you make an accurate measurement, an accurate reading. Okay, so today we're going to talk about the law of mass conservation. The law of mass conservation, according to edition 3 of Apologia, is that matter cannot be created or destroyed. Matter cannot be created or destroyed. It can only change forms. Something that I would like to add to that is that in any chemical or physical process, the total mass of everything involved must remain the same. I'm not going to expound upon it. I'm going to show you this in an experiment. And I want you guys to think about that definition and make a hypothesis, an educated guess. So what I want you to do is get out your notebook, and I want you to notebook throughout these 2 experiments that I'm going to do. Hopefully I don't lose any of this footage. I might have to pause some during the video because of my kids running around. But we're going to do 2 experiments. The first one is going to be on the conservation of mass, okay? So in order to make this happen, and let me see if I can flip this camera around. No, I just took a picture myself. Hold on one second. My Android's not probably as good as an Apple. Okay, for what we need, the list of things that we need for this experiment is a watch glass, spelled like a watch you'd wear on your arm or as you watch out for something. We're going to need a 250 milliliter beaker. We're going to need a 100 milliliter beaker. We're going to need some vinegar. We need some milk, which I have here. And we also need a mass scale, which I have here. And it's going to measure in which unit? Grams. Okay, because that's how we weigh or measure mass. Okay, so we're going to use these items to perform an experiment. And don't forget goggles, okay? So I want you to write the date. I want you to write your name and my name, Mrs. Boom, Mrs. Rose Boom, Miss Kim, whatever you want to put. And write down your list. I want you to write down the purpose of the experiment, which is to investigate when a chemical process happens, whether the mass changes or stays the same. That's the purpose. Then you need to have a hypothesis, an educated guess. When a chemical process occurs, I think that the mass will change. I think the mass will stay the same. I think the mass will grow. I think the mass will get smaller. You need to have your own hypothesis. What we're going to do is we're going to weigh our milk and our vinegar separately. Then we're going to weigh them together after a chemical reaction has taken place between the 2 and see what happens to the mass. Okay? So you could even say when vinegar mixes with milk, the mass gets greater, or the mass stays the same, or the mass becomes less. So if you need to pause your video, write that stuff down. Okay, make it look just like I showed you guys 2 weeks ago, week and a half ago, in your notebook. Now I'm going to go through the steps, okay? So what I'm going to do, and I'm going to set my camera down here. I apologize for the angle. We've tried this so many ways and it's just not going well, so I'm just trying to get it done for you guys. Okay, I am going to take this larger beaker that I have here, the 250, and I'm going to put in 50 mLs of milk, approximately. And this one is marked off by 50s. I'm going to try and find some beakers that are marked off better for us. I wish there were more lines, but that's okay. We're just high schoolers. Okay. So there's the 50 mLs of milk, okay? Now, I'm going to then put in 30, approximately, mLs of vinegar into the 100 milliliter beaker. This one's marked off by 25, so it's a little bit trickier. I'm literally guessing. It's my best guess. Okay, we're gonna go with that. Now what I'm gonna do is turn on my scale. I'm gonna make sure that I've pushed the tare button to make sure it's at 0, and it is. I'm going to place the 250 milliliter beaker on first, as you can see. And then I'm going to put on my watch glass. And then I'm going to put on my 100 very carefully so that they don't fall. And we're going to see what the mass is. Can you guys see that? 270.7 grams. That's the weight. So you need to record that weight. And of course, you're writing down step by step what we do. You can do it all now or do it all at the end. I don't care which. 270.7 grams is the weight. So now what I'm going to do is carefully remove each of these items. And I'm going to pour the vinegar into the milk container. And you can see this is just good old regular milk. The vinegar has been added. I'm going to wait 5 minutes to see what happens to this for the chemical reaction to take place. In the meantime, you can write down these steps that we've done. You can also look at my cool poster that Audrey made for me for Mrs. Boom's class. We've introduced the law of mass conservation, which was first reported by Antoine Lavoisier. Am I saying that right? I don't know. I like to say it though. This guy first came up with it. He's generally given credit for the formulating of this law. He was a philosopher. They used to call scientists philosophers. You don't want to know what we call philosophers today? Not all of them. I shouldn't say that. That was mean. Don't listen to that. If you take philosophy at a secular school, you'll see what I'm saying. If you take philosophy from Mrs. Sawyer, you'll think she's swell, because she is. And she's a good philosopher. All right, so now we're doing our conservation of mass experiment. I was going back over significant figures. I'll be right back. Okay, I'm back. I wanted to tell you guys that when I'm measuring in these beakers, for example, since one was marked off, the 100 is marked off by 25s, and I put 30 mLs in there, right? You would just put 30 because it's marked by 25s. Don't put point anything. And then with the 250, I put in 50. Just keep it at 50 because, again, it's approximate by 50s. Okay, but the scale is precise. We don't need to change it. It's digital. If I was using this other one, then we would have to do some guessing there. Okay. We might need to put a 0 at the end of the scale, though. I need to look into this. I'm sorry, you guys. I'm rusty on this stuff. And did you notice the whole time I did the experiment, my goggles were on my head? It's about like me and wearing my face masks. Okay. So now what we're going to do is I've let this mixture sit for approximately 5 minutes to let a chemical process take place. I don't know if you can see this. I'm trying to let you guys see this. I just want you to see what's going on here. All right, can you see that? Can you see the milk? So basically, I'm trying to focus for you guys. It's a yellowy milk anyways because it's fresh. But it's got some white action going on. You guys are never going to want to have school like this with me again, are you? It's horrible. Okay, so there's definitely a chemical reaction taking place. There's some curds happening here, okay? So now what I'm going to do is I'm going to stack everything on here, and we're going to weigh its mass again. So, I'm going to turn on my scale and make sure it's at zeros, and it is. I'm going to put on my 250. I'm going to put on my watch glass, and I'm putting on my 100. And we come up with 270.8. Wasn't it 270.7 before? Very, very interesting. So it changed barely, 1/10 it changed, but to be honest, it shouldn't have changed at all. So the milk did curdle. Usually we think of, you would think of curdles like cottage cheese as getting much heavier, but what?
Where's Lincoln?
I don't know. I think he's making bracelets. This is how you homeschool with 7 kids. It doesn't, you think of something curdled as being heavier, okay? We think of solids as a heavier liquid. So you would think that the curdled milk with the vinegar mixture, that before they were mixed, when it was just liquid, that it would be lighter and then it would get heavier, okay? But the mass indicated that really it didn't change. That last figure has some uncertainty in it, so the 0.1 change doesn't matter. Now, if it would have jumped up a whole gram, that would be something. Or if it had went down a whole gram, that would be something. But that last digit, the 0.7 to 0.8, it's the one that, how do I say this? It's uncertain, okay? So, essentially it didn't change. So what was your hypothesis? Were you right? Were you wrong? Now you need to make a conclusion, okay? And you need to write that down. So finish that up, and then we're going to do another experiment. I'm going to pause the tape. So I want to read a little snippet to you, okay? Generally we think of solids. I'm taping. What are you doing? Literally. Generally we think of solids as much heavier than liquids. So that's not the case here, though, okay? According to the law of mass conservation, the mass doesn't change during a chemical process, okay? So from a scientific point of view, measurements that differ slightly in the last significant figure are the same. So despite the fact that a solid formed, we did form a solid. If we let this sit here all day, it'd be nasty by the end of the day. The solid is forming from 2 liquids. The mass was the same both before and after the solid formed, and that's the conservation of mass, okay? Even though the appearance of the system changed significantly, the total mass did not change at all, which is actually pretty amazing. I think I'm going to leave this sitting out here on my counter all day and weigh it again later, and I'll tell you guys what happens then, okay? So this is important in chemistry because there are times when you can't see some of the substances that are involved in a chemical process because they're gases or things your eyes cannot see, okay? So I'm not going to get any more into that because I'll spoil the next experiment. We'll talk more of that after the next experiment, which I'm going to set up right now. So once you finish notebooking that one, we're going to move on to a second experiment. Same date, same team member names, okay? This experiment, though, is called... Wait. How do you like that? Play on words, okay? So get your notebook out. Next page. Wait. The purpose of this experiment is the same. We're going to observe what happens when the chemical reaction takes place. Again, okay, with the mass. But this one's going to be a little bit different. So let me get my stuff set up here. One moment. Okay, folks. Same, I'm going off memory here. Same premise for this experiment. Your question can be the same. Your hypothesis, you may have a different hypothesis this time, okay? Maybe not. Maybe you had the same hypothesis, you want to do it again. Maybe you were right. Maybe you're super smart. You don't need to be taking this class, you need to be teaching this class. All right, so what we're going to do is, with this experiment, we're going to have some different items. I've got this flask. I've got a 2-liter bottle. I've got a 1/2 cup measuring. I've got a 1 teaspoon measuring. I've got vinegar again. Got baking soda, everybody's favorite, vinegar and baking soda. And we've got our mass scale again. All right, so this time, what we're going to do Do we have a rubber band?
Does the bracelet making kit one work?
I don't know. We may not need it. We may need it. We may just use our fingers. I'm going to see if we can find a rubber band. You go see if you can find a rubber band in a desk real quick, okay? In the meantime, I'm going to use the funnel. Oh, a funnel. Funnel. And one more thing. I'm so forgetful. A balloon. But we were going to use a yellow balloon. Okay. There's the yellow one. So what we're going to do this time is I'm going to use this funnel to pour 2 teaspoons of baking soda into the balloon. Goggles on this time. This is a little tricky. Okay. 2 teaspoons. Did you find something? Just wait. Come on over. One. You want to pour this one in for me?
Wait, should I have on glasses?
You should. After you pour this, you can go get them out of that bag, that blue bag down there.
Oh, hold on, there's still more.
Oh, get it all in. Definitely get it all in. Okay. So as you can see, I've got 2 teaspoons of baking soda inside of my balloon. Okay, we're not clogged up. It all passed through. I can see through the funnel. Okay? Now, I'm going to have my assistant hold on to this for me here in just a second. I'm going to pour half a cup, which is about 120 milliliters of vinegar into my flask. Ooh, this is scary. Ah! I'm in a mess. Ugh, that stinks. Let's see here. I'm just going to look at my flask and measure. This is a really weird flask. Okay. It doesn't have to be exact, to be honest. You can say that I poured half a cup, 120 milliliters of vinegar into the flask and some of it spilled, but that's okay.
Now our table smells.
Now our table smells. Okay. And this is where you can do the experiments over and over, right? It's kind of fun. Okay, so now what I'm going to do is we're going to attach the balloon to our flask, but we're not going to make a chemical reaction yet. I don't know if we're actually going to need that, E. Okay.
I've done this, I just held it down.
But I don't want my vinegar. Okay, we're good. We don't need it yet. We don't want our baking soda to go in yet. I'm going to weigh this. So again, I'm going to turn on my scale, make sure it's at 0, and it is. And we're going to record the weight, the mass, my apologies. 275.8. Can you guys even see that? I have no idea.
I can see it.
Trust me, 275.8 grams is the weight, okay? Now, we're going to make the chemical reaction take place, okay?
Do you need the rubber band?
I don't think so. I think I'm just going to hold it.
Okay.
Thanks for getting it, though. Okay, so what I'm going to do is I'm going to tip the balloon's contents into the flask. What do you think will happen? Holy smokes, I'm slightly concerned.
If it bursts, I don't know what will happen.
You guys see what's happening? Oh boy. It's a good thing I got these goggles on. This is awesome. I love science.
Is it?
Okay, wait, we're recording. You can be in here. It's fine. All right. So, you can see that we just had a reaction take place. I'm going to let go and we're going to weigh this. 273.2. 273.2. Did it get lighter or heavier or stay the same?
Me?
Yeah.
Lighter.
It got lighter. But wait, the law of mass conservation says that the mass doesn't change in a chemical reaction.
So they're liars.
They're liars. Emerson says they're liars. 273.2 grams. Do you have any thoughts? If you have a sibling, talk to them about it. If you don't, talk to yourself about it. What do you think?
I think I've done this. I already knew it was gonna happen.
Why do you think it weighs less when it said it would not?
Because all the baking soda got poured into here, and then it all just like dissolved in the vinegar.
I'm going to tell you, we know that the law of mass conservation has to be tried and true, right? This thing has been around since the 1700s. Lavoisier came up with it. You do need to know that, people, for the test, okay? I'm giving you a clue there. We know that there are multiple things needed in a chemical reaction. Sometimes you can't see all the things being used. Is it possible that there was an invisible substance that was necessary for this reaction to take place?
Mm-hmm.
One that we cannot weigh because we're just high school scientists. All right. I'm going to read something to you, and then tell me what you think. Okay? Early chemists would watch wood burning. Who has watched wood burn? I know all you boys have because you are little pyros. Right?
Mm-hmm.
Yes. Okay. When wood burns, you've got wood. You light it on fire. What happens to the wood?
It goes down into ash charcoal.
Is a log heavier than a pile of ash?
No.
Is a log
Well,
heavier
yes.
than a pile of ash? Yes, it is. Okay? Now, here's what's happening. When you want to light a fire, what do you have to have? Something you can't see. Starts with letter O. It's on the period.
Oxygen.
Oxygen. You have to have oxygen for a fire to burn. When these guys first were watching the wood, they weren't thinking that there was something they couldn't see being utilized in the chemical process. Okay? It was later in time that they were like, oh, wait, there has to be something else involved here. When we snuff out all the oxygen, we cannot have a fire. Therefore, oxygen is necessary to burn wood. Oxygen is a part of the total mass of the chemical reaction that's taking place. Okay? So early scientists would watch the wood burn. They were unable to see the carbon dioxide. They were unable to see the water vapor that was forming from the wood because those substances are colorless and they are gases. So as a result, they simply thought that the matter in the wood was disappearing. They thought the wood disappeared. Matter was being destroyed. Okay? Because their experiments were not accurate, early chemists developed scientific laws that were very wrong. Today, we've developed methods that allow us to detect the presence of colorless gases. So, we can measure the mass of the carbon dioxide, the mass of the water vapor produced when the wood burns. We can determine that when wood burns, the oxygen in the air around the wood is used up. That's why fire cannot burn unless there's a plentiful supply of oxygen. So, if we measure the mass of the wood and the mass of the oxygen before a fire starts, and then if you can trap the carbon dioxide and the water vapor that are produced by the fire after it starts, then we will find out that the mass of the wood and oxygen used by the fire is exactly equal to the mass of the ash, the water vapor, and the carbon dioxide produced by the fire. Isn't that awesome? So first you'd have to measure the mass of the wood and the oxygen. Then you would measure the ash, the carbon dioxide, and the water vapor, and they would both be equal. You would have a balanced equation, and the law of mass conservation would be truth. Okay? So, in this experiment, since it got lighter, we can understand there must be something else being utilized in order for this experiment to take place. And since you can see that the balloon is blown up, I mean, think about the balloon. Is it you think something can escape through this latex?
Hmm.
I bet something can.
Well,
I don't think everything can stay in it. I don't think it's foolproof, right? Like some little
would
tiny,
it
teeny
deflate
holes.
if you left it?
I don't know. Would it deflate if I left it? I'll leave it and we'll find out. So what I want to do now is try this experiment in a different way. Emerson, go get me a blue insert for a medicine plunger. The blue insert.
This
Okay.
insert?
Just the insert, the blue part. We're going to try this a different way. I just thought of this. This, my friends, this is science right here.
Big one or small one?
Biggest as you got. Okay, I'm going to see how much baking soda I can fit inside of this blue plunger. Okay, this is going to be really tricky, actually. That's not going to work. Do you have the smaller one? You get the smaller one.
This big one.
Do 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 do. Do 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 do. Do 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 do. Ah, yeah. Okay, sweet. We're gonna see how much baking soda we can fit inside here. Okay, Emerson. You guys can totally write this down if you want.
Should I do this over something?
I should totally do this over something. You know what? Funnel. Cam, get me a smaller metal funnel. You know what I'm talking about? So what we're going to do this time, because that last time that we did this experiment, I put the baking soda, is that the smallest one I have?
No.
Get the smallest one I have. I put the baking soda directly into the balloon. I wonder if some of the baking soda got stuck to the sides of the balloon. I don't know. There's a lot of variables here. I'll tell you this. I did feel my fingers got wet. Some liquid came out the sides of the flask. Okay. So what we're going to do this time is we're going to try to trap the baking soda in here. I'm not going to let anything touch. I'm going to use this 2-liter bottle. Now I did notice something when I got this 2-liter. It appears that there could be a slight hole in it. I think there's a slight hole in it. Do we have another empty 2-liter bottle?
That one does have a hole in it.
Bring that thing here. Whatever you have, bring it here. Whatever you have, bring it here.
We need tape.
You can size it.
But I need it to be skinny. I'm going to pause the tape, guys. Okay, so I'm going to try this with the 2-liter. I also have this. And you could change up all your bottles, but I'm going to use a funnel. If I use this water jug, I'm wondering, yes, I can fit in more. I'm going to use this first. I'm going to use this. So if you want to write this down, you guys can. I'm going with 1 teaspoon right now. I'd like to keep my measurements the same because you don't want to mix up a bunch of variables. I'm really making 2 variables right now, guys. I changed 2 things. I shouldn't do that. I'm using something to hopefully keep the baking soda into it for a bit of time.
Bring me mine.
Okay, this isn't all gonna fit. Okay, it's just 1.5. I got half of that last teaspoon, so 1.5. Okay, that's all I could fit in here. Now, I've got 1.5 teaspoons, approximately, 1.5 teaspoons, which would be the same as 7.5 mLs. 7.5 mLs. And what I'm going to do is I'm going to put half a cup. I'm trying to decide which. I'm going to go with the 2-liter. Okay, I'm going to use the 2-liter. Half a cup of vinegar into the 2-liter. Emerson, you're going to hold this.
Wait, but when she
Just hold it. Just hold it. What and I need what?
The smaller one now?
That is the smaller one.
No, it's not. This is the big one.
It is?
Yeah.
Oh, well then we have to use the jug. We have to use the jug of water. Okay. Here we go. Half a cup of vinegar. Now I'm going to try to drop this in here, vada capale, so that no chemical reaction takes place until I want it to. I failed! It's already fizzing. It's already fizzing, guys. That's not going to work. They had some cool little thing on a video I watched where they could do that. All right, that's okay. We just won't do that one. Now we're going to use this bottle that my boys just emptied because they were super excited at the thought of emptying a bottle. Nope, wrong thing, Miss Kim. Half a cup of vinegar into the 2 liter. This is so scary.
Making a mess or the experiment?
Making a mess. It's all right. That's why it's approximate. This is more for fun. And I got my scale wet. I hope this thing's water resistant, vinegar resistant. Okay, make sure that's level. Hold on, we'll use the bigger one into a balloon. Okay, E?
Oh.
All right. And we'll weigh it all and we'll see what happens, okay? All right, pour it in. One more. You can watch it.
Come get some.
I'm attracting a crowd. I'm becoming popular. Everybody wants to see what I'm doing. I'll do this again with all my kids.
I'm just watching your messed up hair.
Okay, so we've got 2 teaspoons. We have the same measurements
Damn it. Hit me with another glass.
of vinegar, same measurements of soda. I'm going to turn on my scale, pray that it still works. It's at 0. I'm going to put this on the 2 liter. And I am going to, I'm not going to use rubber band because I didn't last time. That'd be another variable. I'm going to weigh it. 177.4 grams. Help me remember that number, people, because I keep forgetting. 177.4 grams. Are you guys ready? Woo! It wants to move off of my thing. 175.3.
177.4.
175.1. 175. 174.9. So what gas do you think is necessary? I mean, really, there's only one that I can think of. Hi. Would be oxygen. 174.9 grams. I'm guessing that oxygen is being utilized in this experiment, or if not,